Thank you, Rob. Thank you, everyone. Hi, everyone. Good morning, good afternoon, good evening, wherever you are. And thank you for joining this seminar today to attend this talk. I'm very pleased. I'm very happy to be back here at Gerard, and where I spent many years. This is maybe one of the rare times when I see the room from the other side. I'm usually sitting there, and I'm happy to be here today. So thanks to Gerard and Professor Zakwa, I'm able to give this talk today about this paper. Let me remove this. Today I'll be talking about a topic that is more into economics than game theory, but the game theory is used here as a tool to solve the problem. So the talk is titled on the impact of cross ownership in the common property of renewable resource oligopoly. This is a joint work with Miao and Professor Benchekroun. Miao did his PhD with Professor Benchekroun here in Montreal, and one of his papers was about cross ownerships. And this paper is a kind of extension to that paper, where we're going to talk about renewable resources. So since I did my PhD in renewable resources as well, so it's a good combination of the topic. Please feel free to ask me questions during the talk and stop me anytime. The calculations are very heavy, so I'm not going to show a lot of calculations, but I will go straight to the point and try to introduce how we came up with a contribution for this problem. Oui, sur cliquer ici, je pense. Après, ça devrait marcher. Ouais. So the overview of the talk is I'm going to introduce the problem, then we're going to show you the model and why we chose this model, and then we're going to look at the results. The results are twofold, are either on the short run or the long run, because we're considering here an infinite horizon. And finally, in terms of conclusion, we're going to discuss what's happening. Right now in the world, there is a phenomenal growth of cross ownership, which means that we have some firms in certain sector, not all the firms in the same sector, but some of them, a subset of all the firms will acquire share in rival competitors and participate in various forms of cooperation, for example, joint ventures. So we're going to call the K will be the subset of the companies or these shareholders, and N will be the entire team or the set of players. V will be the share of the share that they hold in each other. So I'm starting with notations, which is very unusual, but this is the only way I can do it just to introduce the problem. So this problem of cross ownership is growing across every sectors almost. And anyway, automobile, banking, media, electric powers, insurance. I'm going to give you an example here. So, for example, in the automobile sector, we all know this famous story between Nissan and Renault. So they instead of merging together, they hold shares in each other's, and we have 15%. And then we have another thing, which is between Nissan and Mitsubishi, where Nissan holds 34%. We have another example between Toyota, Mazda, Suzuki, and Subaru. So you can see that the shares they hold are small, right? It's not very big, so there's no control, but there is kind of let's say trick here to try to increase the profit in some sense. So the closest example to the story in this paper will be somewhere here. If only we had another arrow going the other way, and the entire all the shares will be the same. Okay, so if you have like 20% everywhere, and we have another one with 20%, that's the story we are looking at here, knowing that we have other companies in the market that they don't hold shares in this trio of companies. So back to the theory. In the static oligopoly theory, in a static kernel, for example, homogeneous products, we always know that, by the way, I'm going to call the I and the O. I will be the insiders, the K firms, and O will be the outsiders. And the insiders are those who hold shareholders to each others, and the outsiders will be the others. So in a static homogeneous product model, we know that the quantity or the output from the insiders will decrease. It's like getting closer to monopoly power, monopoly practice. But then the outsiders, from game theoretical part, they will look at what happens. Okay, we can increase our production. That's what happened. But in totality, the total quantity, which is the sum of both, will decrease, and then de facto the price will increase. This will result in a decrease in the consumer surplus, but will be accompanied by increase in producer surplus. That's because we have higher prices, less quantity, and the totality will have a deadweight loss, and the wealth or the total output or total surplus will decrease. And this is normal or very basic 101 monopoly theory. But there exists a cross-ownership paradox, which is similar to the merger paradox, where companies merge, which is, it looks like it's profitable, but it's shown in this paper that we're extending right now, that it can be unprofitable. So we may buy shares from each other, but we can lose some money. And especially if we have the number of if we have K over N, which is the share of the companies, the firms that are holding shareholders in each others, is large enough with a moderate or small v, which is the share, we can have this paradox happening. This is just an example of what happens. So, for example, this is the profitability, which shows that the higher the number of players and they say the cross ownership holders, the lower is the profits, and this comes from the paper we're extending.
So this K and I mean the ratio. I mean the only ratio that we care about is K by N, not about how much share you own in a company.
We do V.
Okay, this V is small enough.
Yeah.
How small is it?
Well, it depends. It's not. There's no one specific number, right? So
for those plots that you showed, what is V?
I think it was 0.5, very small, 0.10 maybe, 0.10%. So this is not what we found. This is what we are looking at from the paper we're extending, actually, just to prove that it's happening. So the only takeaway here is that for a certain number of K and N, and for V, we may have this paradox. It's not always the case, but this is what's happening. This is what's happening shown here in this paper. So it's not because I'm going to look for a certain partial merger, like partial merger, and then it doesn't mean I'm gonna get more money. We may have cases where we lose money. So this is one of our motivations to see if this is gonna be is this hold in a renewable resources environment. Good. So this is our resource question here, which is can the predictions from the static theory still hold in a common property renewable resource industry where the resource stock, if unexploited, keeps reproducing? And the best example, since I did my PhD in fisheries, will be fishers. So cross-ownership activities are absolutely prevalent in, for example, cooperation between fishers. We have some examples from New Zealand, from Iceland. Examples exist almost everywhere in the world where companies buy from each other's parts and shares, and then they're looking for a better profit. And this is happening a lot in fisheries. We have some papers by Colombo and Chula and Antonio as well. They have discussed this problem. The second research question is what are the competition policy implications of cross-ownership in renewable resource industries? So first is legally viewed as partial mergers, but it is less detrimental. Like we don't care about it a lot. We say, oh, it's not merging. It's just like people are buying shares, but that's it. So merger regulations apply when cross-ownership links involve corporate control, which means when we have high share, which is like more than 50%, like 60%, 70%, when you can influence what's happening in the decision, and when you can tell the CEO of the firm what to do, and that's where we use the merger regulation. So firms might consider cross-ownership a more appealing corporate strategy and adopt it disproportionately. So in this case, the firms would say, okay, so what we're gonna do, we're gonna find a way to overcome this viewed as partially merged, and then we're gonna jump into cross ownership, and then we're gonna look for a better profit and practice something as close as possible that we can do for a monopoly practice. But there is a growing consensus among policymakers right now. They think that, or they should be thinking that we may need to be more strict with this practice. Yeah.
So here, when two firms are like doing this, like buying shares, what is the reason? Can they control each other's quantity or price? No, right?
No. Well, we cannot control each other's price, but the price is at the market. It's given, like usually it's given. So what happens is that when I buy shares from you and you buy shares from me, it's kind of, we're getting one step maybe away from perfect competition, getting closer to the monopoly. So what we do is like we influence each others, and then we're gonna see how it is more. It will be more clear when we see the profit. I know that you could some mathematics here, but the profit we will see that when you maximize your profits, you will take into account that others have shares in each others and some other profit. So that's will play a role, and then we can see how we're gonna practice something that is closer to the monopoly. So for others, if you have any questions, please feel free. I know this is like more economics, but it's very simple.
We are waiting for the model.
I know, I know everyone is waiting for. First, let's just look a little bit at the literature. So the main contributions in this area, they either provide theoretical framework to highlight firms' interaction. At the research level, we have growing literature on cross ownerships. We have these papers. We have also a large game theoretical literature on the exploitation of renewable resources. We have Benchekroun and Jordan, 2015. This is two other papers that I know very well. The reason I put them here is that they use the same model that we're using in this paper. So, and also I'm advertising some of my previous work. And we have also some policy discussions on regulating cross-ownership links. And there have been some discussions on what they call conservation cartels, which is some cartels they're getting together to influence the influence in the market to not use this cross-ownership practice. But literature is huge here. We can cite everyone. This is just an example. So what we are doing in this paper. So first, we would like to develop the theoretical model that captures both the features of cross-ownership and exploitation of renewable resources. This is very simple. Cross-ownership, renewable resources, what's happening when we have an infinite game, and an infinite game is only possible. I mean, it's possible, not only, but it's possible when we have renewable resources. First, we would like to investigate the impact of this practice on the outputs, like what could be, for example, in fisheries, how much fish or how many fish we are fishing due to cross ownership. Are we fishing more or less? Also, we're looking at the profitability and social welfare. Remember, here we have this theory here that shows that there is a change in terms of profits and outputs. And of course, the most important part here is to look at the short run and the long run, because there is something in renewable resources that when you start, for example, fishing, you may be impacting the resource very quickly. So you need to think what's going to happen later if you keep doing it. So that's why sometimes before reaching that steady state, that is the end state that you're going to be having forever, you need to go through this first state, and that's what we call short run. And that short run is usually different from the long run, and that's why we have two different analyses. And of course, we want to discuss the competition policy implications. So I know we don't do this here, but there are some results. This is in economics, so we have to show a little bit further. So first, we're going to show that the cross-ownership paradox does not necessarily hold when we talk about natural renewable resources. So what happened in other paper may not be possible here. Second, in both short run and long run, profitable cross-ownership can lead to a higher market output and social welfare. So here, maybe we would like to go and encourage such a practice because it will increase our output, we'll have more fish, and also we will have a higher social welfare, which is the sum of consumer surplus and producer surplus, it doesn't mean that everyone will win. Some will win more than what the others lost, but the total will be higher. And then if you have a distribution model, then you can distribute money between the agents, and that's how you can have a better society. Finally, so here, first we need to know what's happening in terms of the resource. Here we're talking about fish. This is a very famous model that has been developed by this paper, Benchekroun 2003. So in the absence of exploitation, so if you don't harvest any fish, what's going to happen is that your growth function, it will have two parts: an increasing part for the stock and a decreasing part for the stock. So for the increasing stock part of the stock, it will be this part here. Delta S, delta is just the intrinsic growth rate, is how, like, for every fish, how many fish we'll have next time. So how many babies do we have? And this part is the decreasing part of the stock, of the growth stock. So the stock will be always growing, but at a certain point, it can grow more. Why? Because there is the theory behind this, and I'm going to show you where this comes from. So I stole this picture online from DFO, which is Department of Fisheries and Oceans, Canada, but this doesn't really belong to them. Maybe the numbers, but this is the theory of the growth of the fish. So what happened is the fish will first grow at a small rate, and then start increase very fast, very fast, very fast, until a certain point here, and then the growth of the fish will break level and will be less fast, until at a certain point, and just grow at the same level forever. So if you take this one here and you look at the slope and you translate it here, you get what we call the logistic growth function, which is this one, and here we have this concave form. So the growth of the function will increase, and it will reach its maximum, which is this point here, where it's before it starts falling. And this is what we call maximum sustainability. And then we'll go lower and lower and lower until it doesn't, the growth is not positive anymore, and just stock stays the same. And that's only in the case of fish. So these are also important, but I'm not going to talk about them. But I just like to put the entire picture, and this is what we're looking at. So remember this here. This concave form, which is very difficult to look at when you're solving models. And what this paper did, which is what helped many people, including myself during my PhD, is that the linearization of this classical logistic growth. So when we had that concave form, it just become a triangle, and then you have two parts, one expanding part, one decreasing part, and that's where we're going to work with. So here, you see that when S is equal to Sy is undefined, but it's just mathematics. Okay. So now this is the part we talk about profits. What's going to happen for the firms? So the firms share free access. So with free access, anyone is free to fish and exploit to produce an output that sells in oligopolistic markets. We call it Kurno because there is no cooperation, nothing, everyone is for himself, and we just sell what we catch. So what happened is that unit of the asset is transformed into 1 unit of the output at zero cost. I catch a fish, I sell it. I don't have to do any transformation, anything. So this is an assumption just to get rid of more.
This is the way of selling fresh fish.
Exactly. So let's think about the guy who's just fishing and comes to the shore and sells his fish, and immediately you eat it. So the inverse demand function for the output has this very usual form, which is constant minus BQ. Q is the total harvest, and of course is the sum of the harvest for everyone, for the end players, right? So this is the price. The price will be depending on the quantity this way. So now we have the subsets of the players, which is K. That could be everyone, but we prefer that it's not everyone, so we can see what's happening. So they engage in cross shareholdings, while the other firms remain independent. So they do whatever they want. They just look up. We can call them the left out players for those who are familiar with the characteristic function literature. So the left out players, they will just do as usual. So here's the profit. The profit of these insiders. First, there is their profit, whatever they fish or harvest, they sell it. Pi is P times Q, plus the share of all the others' profits. Okay, so this is my profit, and the share of it will go to others. Okay, and share of it will go to all this K. So V times K times my profit will disappear to the others, but I will get more something. And if you replace, you will P plus Q, P times Q, which is my profit, plus the share of all others. Where V should be in this range, cannot be bigger than 1 over Q minus 1. Think about it. If we have only one player who is holding a share in himself, it doesn't work. It's just going to be undefined. If we have two, so V can go between 0 and 1 is going to be total. So if we want no controlling, means like I hold less than 50%, K should be 3. So 1 over 3 minus 1 half. So that's why we want to have this assumption here, and this condition will help us to solve the model easily. So we avoid any extra cases. There's so many cases in this paper that you need to get rid of most of it you can when you build the model. So now we have a non-cooperative differential game. After a few manipulations, we end up with these two maximization problems. There's one for the insiders and one for the outsiders. This is the easiest way to see it is to look first at the outsiders. It's just the profit, P times Q, okay, is the discounted form of it over the infinite horizon. So between brackets is P, okay, remember, and times Q. Now we have the same thing here, but it's more complicated. You see? Okay, wait. Some of the people also. Okay. The outsiders' profits is the same as insiders, but there's more to count for thanks to this part here. And if you replace, for example, V by 0, then K, V by 0 will end up here. Just an example, this will be 1 times the Q, and then you can have. So that was also a way to make it easy to solve the model, is that every time we put V at 0, and then we look what happens. Is we go back to the other case, then it's and then of course we have stationary Markov feedback strategies, where we call it phi. Here the resource is growing at this is the same here. It's just that we write it this way. The here is the same as here. It's just this way, well, this way with Q, and this way with Q, but just we like to see who we're talking about. Okay, so here's my point. So we're gonna jump first at what kind of strategies we have. So first, let me show you the results. So this is what we get for the insiders and this is for the outsiders. We're gonna have 3 levels. First, we don't fish anything when the resources are very small. When the resource is starting to grow until a certain level, this will be the strategy, and it will depend on S. And after that, when it gets very high, it will be constant, okay? And that's what we have here, the 3 regions. So we have no fishing at all, because the stock is very small, you don't want to deplete it. Then we have a growing fishing strategy until a certain point when it gets very abundant, then you stagnate, okay? That's what explains this form. So S1, we call it the maturity threshold. S2 is a threshold beyond which firms commit to the static kernel strategies, which we cross over. So we keep going. So here, first thing to see is that we have the strategies for the outsiders is higher than insiders, which is normal, again, because why? Because insiders will think more like to the direction of monopoly, and then they will decrease their their harvest, and then outsiders will see that they can do more, and then they start to harvest.
How is your model different from the previous model, the one that you had that's already published?
We
You
can.
were saying that it's the difference is between renewable renewables and natural.
Yes. So where is it? So this is the model for cross ownership. This is the one without cross ownership. So when you see C is without cross ownership. So here we have two types of strategies. First, actually, it's more just here they don't take care of, they don't account for the share of V. So the V will play a role.
Okay.
Okay. So it was more simple than I was looking for more complicated answer. So here,
It's obvious that this S2 is the same for everyone.
that was one of the problems, and then yes, it's the same for everyone. Yeah.
It can be proven.
Yeah, it's proven. It's proven the paper is the same for everyone. This is one of the things that took more time to prove, and yes, it's true. So what kind of solutions we're gonna have? So remember, we have this growth function, and now we have the strategies, and then we'd like to see what's happening in terms of statistics. So we have two cases. For example, if we go here, we can either go on the top or cross here. So that's what I'm going to show you right now. So either we have one steady state, which is this case, where we have this level of the strategies is higher than this delta S, which is maximum sustainability rate. Then you're going to have only one time we cross this function, and this is your only steady state. So it's and it is stable. Here, if it's under delta Sy, in this case, you have three steady states. It's where the red and the blue cross. So you have this one and this one, they are steady, they are stable, but the S2 is not stable, because here what you're gonna do is just gonna fish at a certain rate, and then you're gonna come back to this one infinity. So these two cases that we worked with. So now, what's happening in terms of the effects on short run and long run? We start with the first with short run. So there exists a scenario in which the insiders will increase their production. So which is really new, or not new, but this is one of the things we were looking for. And then there's another situation where the outsiders will decrease their production. So here, if we think about it, we are not just only depleting what's there. We're trying to control what's going to be in the market forever. So, for example, this one, insiders increase. So we see that here. So in red first, in red is without cross ownership. So here, you see, we will have a higher strategy than when there is no cross ownership. So what we would like to look for now is this level, this one hat and this two hat, and see this this part. So when S2 is between these two, then we're gonna have this case. The same thing happened here with the outsiders, where they decrease the production, and this is this part. So we would like to find also this S tilde, which is between S1 and S2, that forces the slot to be in this way, so we can have only one time we cross it here and one time we cross it, which means the outsiders will decrease their production. So which is counterintuitive, because as usual, the theory says that if you do such a practice, you will have that the insiders will decrease their production and outsiders will increase their production. So these are some cases that exist in this paper. So why this is happening? Because we have two channels through which the cross ownership will affect the extraction rate, or what we call the harvest rate in this case. So there is a competition at the output market level, which is where we sell, for how much we sell, and there's also the interaction between firms at the reserves level. Okay, so we want to have this tragedy of the commons is happening as well at the same time that the market is done. This is what we call the static effects versus resource rent effect, which is at a certain point, I'm going to look at how much I value the fish that is still in the water. And I'm not only valuing the fish today, but also the fish today plus the discounted values of all next generations of this fish over the horizon. And that's what creates this dynamic. And then we may find these possibilities where we have counterintuitive solutions. When S is higher than S2, when it's bigger, when the stock is really bigger, very big or very abundant, no resource capacity, and that's only market trend. So when there's so many fish in the water, we don't care about the fish anymore. What we think about is the market. Am I going to extract all the fish and inundate the market with the resource, and then it's going to be just decrease the price? So I don't want to do it. But when S is lower than S2, both market trend and resource trends are into the game. So the impact of rival cross shareholdings on the resource trends manifests as a negative effect for relatively large stocks and a positive effect for relatively small stocks, and positive and negative in terms of if you want to preserve the reserves or not. Okay, and then it will give you more money if you handle it very wisely. We can look at the value function, and this is what we got as a solution. So when we had the feedback strategies here that I showed you already here, and in the value functions, it's also on 3 levels depending on how S compare with the stock with these levels. And then you can see the most important part here is to see that the derivative of V, or the value function with respect to the stock, is how much you value one extra unit, or the marginal value of an extra unit is negative because A is a negative term. And here also, if you look at S, if you look closely, you will see that it is negative. Okay, so the value will always be negative when S is slower than V, but then it will be 0 when we reach an abundant level of stock. Whenever you go across or past this S2, you will not give any value to the fish, but this should be like a high, very abundant level of the reserves. So if we look at the industry outputs, how much you produce or how much you fish or harvest, then we can compare what we do with cross ownership and without cross ownership. And we see that sometimes you harvest less, sometimes you harvest more, and at the end you are harvesting. So what brings us to one of the propositions of the paper. Unfortunately, I couldn't show everything. So for any n higher than k and v between 0 and this condition that we already set, there exists a threshold of S, or the stock, that belongs to S1 and S2, and another one, S2 tilde here, belongs to this S2 and S2n. So whenever you see n, means that there is no cross ownership, just large corner or corner. So C is for corner, such that we have the strategies with cross ownership is higher than the strategies without ownership, if and only if S is between these two. So literally, we're looking at this level of the stock here that will force us to have a positive difference between the blue and the red, which means I harvest more under cross ownership than no cross ownership. But in general, I will always be less. So these small things here, that's what we were looking at in this paper. Like what's happened, how it happens, where, and we can prove it or not. So in terms of private incentives, can the situation of industry output expansion ever occur as firms may never find it profitable to engage in rival cross ownership, cross shareholdings in the first place? So we need to look at what happens in terms of profits. We need to look at profitability analysis and say, okay, I'm going to take this decision to maybe go for cross ownership or not, depending on how much money I'm going to get. At the end of the day, for firms, what counts the most is how much profit they're going to make. So first, we're going to assume that rival cross shareholdings occur only at the time t equals 0, with S, which is initial stock positive, and this short haul is irreversible. It stays forever. So we don't change it. We decide today, which is a very strong assumption, but it helps us to understand what's going on in these situations. So here we can show that there are some parts of the, this is just an example, numerical example. So sometimes we had to plot these numerical examples to understand what's going on. We can see that, so this is the profit or profitability. So this is the line. So we can see for certain levels of V, it's always positive, but for others, it can go negative. But first, we have this positive jump at the beginning. So that's also one of the cases that encourage us to keep going and look for why it's happening. So now, what drives this difference in the short run? So there exists a direct physical link between the rate of exploitation and the remaining common stock of the sets. So we have decision variable and state variable, which is a very common dilemma. And we can link it to the Hassan model, for example, how much you want to keep in the water versus how much you want to harvest and put the money in the bank, depends on how much you would like to go. So, and of course, for game theory, it's a model, there's players. So an action by one of the players that changes the level of the stock has an effect on the decision of all its circles, definition of interactions. So the outsiders may react more immediately and in some instances also reduce their output. So this is what we found here is that even though you are not engaged in cross ownership, you may take that as a sign and say, okay, I may decrease as well my production just because I know they are going to do so. So that will help for infinity. So for some interval of the stock, cross ownership can lead to an increased valuation by each player for the marginal limit of remaining into stock. So there are some intervals of the stock that we were looking at that the value of that fish in the water will be increased. So we would like to keep it, and that's why we would like to decrease your harvest or output. So that's why I said today is going to be more like in economics, but we can see also the application of game theory in economics. So of course we had numerical analysis, and this is one of the examples that can show exactly what's happening. So on the top one, the curve here, we have the industrial output. So this is how much you harvest. With cross ownership is the red one, and without cross ownership, the corner one is the blue. So here we can see that there is an increase in harvest here between these two levels. And at the same time, if we look at the output, first of the profit, sorry, first is going to be positive until a certain threshold, and then even negative. So this one here coincides with when it is positive. So we have between these two levels here, S1 and S, we have a positive output, and at the same time, we can increase our harvest. So the thing is that I'm harvesting more and I'm making more money. So that's the thing. And this is because we maybe left some non-harvested at the beginning, and then we can cross at a certain level of to a certain level of stock that maybe will tend to another steady state, and then we have more fish, and then we can make more money. So these are the thing we are showing here. And
so the difference between the blue line and the red line?
Yes. So a blue line is the strategies, how much you fish without cross ownership, and the red is the same but with cross ownership. So we can see with cross ownership in this part here, this is where we cross once and see again. So here we fish more under cross ownership situation than no cross ownership. But within this range, there is some part where the profit is positive and the profit is negative. So where it coincides is here. So here we can see that we have a positive profit is above zero, and at the same time we're above the red. We're above the strategies that without cross ownership. And of course, this is only for the case where k is equals 6 and a is equals 10, and under these conditions. But the goal here was to show that this situation exists under some conditions.
Sorry, I
Yeah.
didn't understand, like, why would you not stop fishing? I mean, why is the profit negative there? I mean, that's what I don't understand. What does mean negative profit?
Negative profit, you are losing money, right? Because it's
Losing or the difference would be this. For instance, difference of earth and not.
yeah, the difference between not doing it, that's the thing. So
Okay,
yeah.
The profit can be positive, but it's an opportunity,
Yeah.
something that.
Yeah.
Instead of earning 20, you're earning 10, but then you're losing 10, right?
yeah,
So
okay,
that's-
now I get it.
Okay. Now, if you look at the long run effects, so now we understand what happens at the beginning of the game or the exercise, then everything can be summarized in this table. So here we have some conditions where the outputs with cross ownership and without cross ownership, how they compare with the maximum sustainability level of the stock. So the only thing here is that delta SY will move. Okay, but these two will always stay the same. So this is without cross ownership. This is with cross ownership. What we can take from this table is that we will always increase our the levels of the stock or the steady state will be higher because of the cross ownership. So regardless of the initial stock, research stock, cross ownership results in a larger steady state asset stock. So we will, in the long run, end up in a situation where the steady state, the stock of the stock is higher. That's one good thing on the long run. So cross ownership increases the industry's output at the stationary equilibrium when delta falls below a certain threshold or is small enough. So here again will depend on delta and also on S0. And reduced competition in the output market due to ownership links makes the industry output fall. So the cross ownership results in a larger long-run asset stocks and is consequently a loss for great industry extraction. But here, if we want to see it on table to make it easy to look at. So here are the cases that will. So if you look at this part here on the top, that's what we showed on the first column of the table. So here we have only one steady state for both. Okay, this one and this one. And we can see the difference between, for example, this one infinity and this one n. When there is no cross ownership infinity, this one is higher. So we end up with the highest steady states and their cross ownership. And of course, we show that by calculating doing the calculations with the limits. Here there is the case. So this case we had only one steady state for both cases. Here we had one steady state when we had no cross ownership, but three steady states when we had cross ownerships. And the third line is when we had both, when both had three steady states, and always we're increasing our steady states for each situation. And this is how we find this. And of course, what I just showed you is for each curve is one of these lines. Okay. So in terms of welfare implication, in both the short run and long run, industrial output can increase following the revolve cross shareholdings. The consumer surplus can increase as a result of cross ownership. The industry profits can also go up, so they can make money. Cross ownership can be welfare improved. Okay, that's one of the results we had in this thing. So strict policies that restrict cooperation among users of common pool renewable resources could ultimately harm consumers and society. And unintentionally, these measures might produce the exact opposite effect of what is intended. This reminds me of one of the very simple ideas we have in economics, which is the monopoly is the friend of the environment. So when you have a monopolist who will naturally extract less, or he will produce less, then pollute less, or harm the resource less. and then we want to have a monopoly in certain areas of the economics. For example, if you have forestry markets, you would like to have only one person or one company managing this forestry, and that you will cut less trees or fish less fish because it will help the conservation of the resource.
Provided they have an infinite time horizon.
Yeah, so that's why maybe natural monopolist, which is
Huh?
Who does not?
that's a good question, because if you have a natural monopoly which is owned by, for example, by the state, let's say railway or these don't have any time horizon, so they can live forever. So yes, hopefully we have an infinite natural monopoly and not just monopoly. Just to conclude, so the predictions from the static oligopoly theory do not necessarily hold in the renewable resource industry, and this is created especially because of this dynamic of reproduction, this dynamic of if I leave one fish, it will reproduce, will have more kids. If I leave that tree, will grow more and will have bigger. So this Hotland rule in economics is the key that explains what's happened in this paper. Cross ownership can lead to an increase in industrial output, both in the short run and the long run. So there exists an interval of research stocks for which a symmetric cross ownership can be profitable, even though such cross shareholdings are statistically unprofitable. So we just need to pay more attention to this, and we may have cases that cross ownership can be welfare improving, and maybe we can, instead of saying this is not good to have, maybe look at what market it is, maybe it's natural resources, it's environment, and then look at what level of the shareholdings in terms of the V, how much HR is holding from the other one, and at the same time, how many are grouping as insiders and how many are staying as outside. And I think that's it. Thank you. So please feel free to send me an email if you have questions. This paper has been submitted to the Journal of Economic Theory a few weeks ago, and if you have any comments, feel free. I'm sure we will have some reviews, if not with it. Thank you.
Thank you very much.